Hello guys, so this lecture is on chapter 7 of the book, and the name of the chapter is Hypothesis Tests and Confidence Intervals in Multiple Regression. So this is the outline of the chapter. So we will basically be covering 4 different things in this chapter. The first one is hypothesis testing and confidence intervals for one single coefficient, and you will realize that this is basically an extension from the previous lectures, and the same kind of logic will apply even when we have multiple regressors in the regression equation. The second thing that we will do is joint hypothesis tests on multiple coefficients. So basically what we will try to do is that since we have multiple coefficients coming from the different regressors in the regression equation, we will be looking at whether a combination of those coefficients are equal to some null hypothesis or not. So that is what we will be testing for. The third thing that we will do is we will look at other types of hypothesis testing involving multiple coefficients. For example, when 2 coefficients can be equal to each other, so we can test those kind of hypotheses. And the final thing that we will do is that we will take a look at what variables of interest are and what constitutes a variable of interest, how to control variables, help in estimating the coefficients of variables of interest, and how to decide which variables to include in a regression model. So the first thing that we will do is that we will start off with the hypothesis testing and confidence intervals for single coefficients. So the hypothesis test and confidence interval which emerge from a multiple regression analysis follow the same kind of logic as for the slope coefficient in a single regressor model. So if you remember from the previous lecture, beta 1 hat is the coefficient which we estimate for the variable x1 in the regression equation. Beta 1 0 is our null hypothesis. So basically what we are testing for is whether beta 1 hat is equal to our described null hypothesis. In most cases we are testing for whether beta 1 hat is equal to 0, and the alternative hypothesis becomes that beta 1 hat is not equal to 0. So in order to calculate the t value or the t actual, we will basically subtract the null hypothesis from the beta 1 hat and then divide it by the standard error of beta 1. Standard error of beta 1 is simply the standard deviation of the variance of beta 1, which is square root of the variance of beta 1. And so this will be approximately normally distributed following the central limit theorem as described before. So pretty much the logic remains the same. You can calculate the t actual by using this formula over here, and when you do that, you can simply see whether the t actual is greater or less than the critical value, the t critical value. If it is less than the t critical value, we will fail to reject the null hypothesis. If it is greater than the t critical value, we will reject the null hypothesis. Similarly, the hypothesis on beta 1 can be tested using the usual t-statistic which I just described, and also the confidence intervals as constructed through this equation over here. Pretty much remains the same from the previous lecture. So you have beta 1 hat plus minus 1.96, which is the t critical value for the two-sided 95% confidence interval, multiplied by the standard error of beta 1 hat, which is your standard deviation of beta 1 hat. So you can do the same thing when you are testing the null hypothesis for beta 2, beta 3, up to any number of regressors that you have in the equation. So pretty much the logic remains the same when you are just testing whether one single coefficient of any variable which is used as a regressor in the regression equation, whether you are testing for a hypothesis for that one single coefficient. So let's take a look at an example, because in this kind of situation the examples will better demonstrate how it is done. So in the first equation there's only one regressor, which is the student-teacher ratio. In the second equation there are two regressors, the student-teacher ratio and also the percentage of English learners in the classroom, and obviously our dependent variable remains the same as from the previous lectures, which is test scores. So in this kind of a situation, the coefficient of student-teacher ratio in the second equation is the effect on test scores of a unit change in student-teacher ratio. But what is important is that this effect is when holding constant the percentage of English learners in the district. So as we mentioned in the previous lecture, we might actually be getting some omitted variable bias problem when if we did not include the percentage of English learners in this equation, because some of the effect of having English learners in the classroom might be captured by the coefficient on the student-teacher ratio. And as you can see, the coefficient actually changes by a lot from equation 1 to equation 2. So you can we can pretty much assume that in equation 1 some of this larger effect was actually the effect of some other confounding variables, some other variables which were part of the error terms, such as percentage of English learners. So given this change in the coefficient for student-teacher ratio, we can pretty much calculate the confidence interval for this new coefficient of student-teacher ratio, just like we would do in the first equation. So we can plug in our coefficient over here, plus minus 1.96 multiplied by the standard error, which is also shown under the coefficient in brackets in parentheses over here. And when we do that, we get this range of minus 1.95 to minus 0.26. So we can see that 0 is not part of this confidence interval, which means that we can reject the null hypothesis that this coefficient of student-teacher ratio minus 1.10 is equal to 0. Similarly, we can do the same thing by calculating the t-stat or the t-actual. How do we do that? We can simply divide our coefficient minus 1.10 by the standard error. So in a sense, what we are doing is that we are saying that minus 1.10 minus 0, which is our null hypothesis, divided by 0.43 gives us minus 2.54, which is definitely less than the t critical of minus 1.96 for the two-sided 5% significance level. And when that is the case, we can reject the null hypothesis that the coefficient of STR, student-teacher ratio, is equal to 0. So this is the result for this kind of an equation, regression equation, estimation of that which we get through STATA. So you have your regression command, you have your dependent variable test scores, you have your student-teacher ratio, which is your first regressor, and your second regressor is percentage of English learners. So you are writing comma robust over here to make sure that you are basically assuming heteroskedastic error term, and in that case it's just always safe to assume heteroskedasticity, because even if there is no heteroskedasticity, the robust standard errors would be equal, the results from that would be equal to the OLS standard errors if there was only homoskedasticity. So this kind of an output from STATA can basically provide us with all the useful information which we need to use from a regression analysis. So all the coefficients are here in this column. The standard errors of all of those coefficients are here in the second column. The t-stats are here, over here, and the probability related to those t-stats are also over here. So we can pretty much see whether each and every coefficient is significant or not, meaning do we actually reject the null hypothesis or fail to reject the null hypothesis that these coefficients are different from 0. So for example, in the case of student-teacher ratio, you can see that the coefficient is equal to minus 1.10, and the probability is equal to 0.011. So we can see that we are basically able to reject this the null hypothesis that the coefficient of student-teacher ratio is equal to 0 at the 5% significance level. But can we actually reject the null hypothesis that the coefficient of student-teacher ratio is equal to 0 at the 1% level of significance? The answer to that question is we cannot, because as you see over here, the probability is greater than 0.01. So if that is the case, it would mean that we cannot reject the null hypothesis at the 1% level of significance. So similarly, you can see the t-stats and the probabilities for all the different coefficients over here, and it will give you a good exercise to actually go over each of these and figure out whether you can reject these at different levels of significance or not. So when we get this kind of a result, we can also summarize this kind of a result by writing down the equation, the coefficients along with the equation, and under the coefficients, the standard errors which are obtained for those coefficients. And as always, we will use the heteroskedasticity robust standard errors for exactly the same reason as in the case of a single regressor. And what was that reason again? The reason was simply that it's always a safer bet to assume heteroskedasticity rather than assuming homoskedasticity, which if there is a presence of heteroskedasticity, will give us wrong coefficients, inaccurate coefficients. So the next thing that we will cover in this lecture is tests of joint hypotheses. So this is something new. We have not covered this in any of the previous lectures. So what we are basically doing is that we are basically testing for two coefficients at the same time. So let's take a look at this equation over here. So the dependent variable remains the same, which is test score. The first regressor is the same, student-teacher ratio, and the third one is also the same, percentage of English learners. We have added this third regressor over here, which is the expenditures per pupil, and so that is what we have added as one of the regressors. So expenditure per pupil as well as student-teacher ratio are both indicators of school resources because student-teacher ratio is usually lower in schools with higher budgets. Similarly, expenditure per pupil would be higher in schools with higher budgets. So if someone actually says that, okay, I want to test whether school resources matter or not, so the null hypothesis then will become that school resources don't matter, and the alternative hypothesis will become that the school resources matter somewhat or by a lot. So how will we write this formally? So the null hypothesis will basically be that beta 1 is equal to 0 and beta 2 is equal to 0. And why are we considering both of these coefficients at the same time? It's simply because both student-teacher ratio and expenditure per pupil are indicators of school resources. So basically our null hypothesis is that school resources don't matter, And on similar lines, our alternative hypothesis becomes that either beta 1 is not equal to 0, or beta 2 is not equal to 0, or both are not equal to 0. So in simple language, if any of beta 1 or beta 2 is not equal to 0, we will reject the null hypothesis that beta 1 is equal to 0 and beta 2 is equal to 0. So once again, restating the null and alternative hypotheses. So a joint hypothesis specifies a value for two or more coefficients, that is, it imposes a restriction on two or more coefficients. What does it mean by the word restriction over here? So like in this example, we are basically comparing two different coefficients, beta 1 and beta 2, so our number of restrictions Q become 2 in this case. If we were comparing three different coefficients, then the number of restrictions would become 3. So if someone actually says that, okay, well, we are testing for the null hypothesis that beta 1 is equal to 0 and beta 2 is equal to 0, so common sense should prevail and we can simply test both of these coefficients individually, that they are not equal, that they are equal to 0, or with the null hypothesis that beta 1 is equal to 0, and then we can test for separately for beta 2 equals to 0 by using the t distribution, or by using the t stats, which you can calculate with the formula that I showed earlier in this lecture, and we can basically compare that t stat that you are calculating with the t critical of 1.96 and figure out whether you reject the null hypothesis or whether you fail to reject the null hypothesis. But the problem in that case would be because you will be doing or testing for these hypotheses of beta 1 and beta 2 separately or one at a time, the results will not be valid. And the reason for that is that when you do it separately, you tend to result too often under the null hypothesis, and I will show that to you in the next slide why that is the case. So if we do the one at a time test, we will have to calculate two different t stats, one for the first coefficient beta 1 and one for the second coefficient beta 2, and we will follow the same logic of calculation of the t stats as in the previous formula. So we will reject the null hypothesis that beta 1 is equal to beta 2 is equal to 0 if we can reject the null hypothesis that beta 1 is equal to 0 and or we can reject the null hypothesis that beta 2 is equal to 0, which would mean that the t stat that you calculate over here would be greater than 1.96 in absolute value, and also the t stat that you calculate from here would be greater than 1.96. So either of the two have to be greater than 1.96, or both can be greater than 1.96. But as I mentioned earlier, what is the probability that this one at a time test rejects the null hypothesis? It actually comes out to be greater than 5% when it should be 5%, because we are actually testing for the level of significance of 5%. So the probability of incorrectly rejecting the null hypothesis using the one at a time test is the probability that you reject the first null hypothesis that beta 1 is equal to 0, and or the probability that you reject the second null hypothesis that beta 2 is equal to 0. So obviously you will have to do 1 minus this probability, and when you do that, you will have to multiply these two probabilities together, because remember the rule of probability when you have to multiply, and that is always the case when you have two independent outcomes. So in this scenario, we are basically assuming that T1 and T2 are independent of each other, and when they are independent, and we are saying that both happen at the same time, we have to basically multiply the probabilities of these two events happening, and then we will subtract that product from 1 to get the probability. So 1 minus 0.95 square, because 0.95 would be the probability of this event happening, and 0.95 would be the probability of this event happening. So 1 minus 0.95 square will give us the probability of incorrectly rejecting the null hypothesis. So once again, taking you back to one of the earlier lectures, that rejecting the null hypothesis at a significance level of 5% means that the probability of incorrectly rejecting the null hypothesis was 5%. So when you follow that same logic, this probability comes out to be 9.75. So this probability is not equal to 5%, which it should be, because we are actually testing for the null with the significance level of 5%. But in this case, when we are doing these hypothesis tests one at a time, our probability of incorrectly rejecting the null comes out to be higher than 5%, comes out to be actually 9.75%, which means that there will be more chances of incorrectly rejecting the null hypothesis, meaning that we will be getting inaccurate results from the hypothesis testing. So the size of the common sense test, which is the one at a time test, is not equal to 5%. In fact, as we will see later on, it will depend on the correlation between T1 and T2, and also thus on the correlation between beta 1 hat and beta 2 hat. So there are two solutions to this problem. So the first solution is something what we call the Bonferroni method, and this is not really part of this chapter, but it is mentioned in the appendix 7.1. If someone is really interested, they can take a look at that method. But on the contrary, the F-stat, or using the F-stat, is a more common practice, and STATA, the software that we are using for this course, actually gives you the F-stat for the tests of hypothesis that the coefficients are equal to 0. So that is the common practice rather than the Bonferroni method. So how do we calculate the F-stat for the joint hypothesis testing? So the formula for the F-stat is over here, is as follows. So T1 is the T-stat calculated for the hypothesis test that beta 1 is equal to 0. T2 is the T-stat calculated from the hypothesis test that beta 2 is equal to 0. This symbol over here basically is the symbol for correlation between T1 and T2, and then once again this correlation is being multiplied by the T1 and T2, the T-stats, the individual T-stats which you get from beta 1 and beta 2. Even in the denominator you have the term for correlation coefficient over here, but if you plug in all the numbers over here, you will actually get the F-stat for the joint hypothesis test, that beta 1 is equal to 0, for example, and beta 2 is equal to 0. Keep in mind that these beta 1 0 and beta 2 0 over here, which basically show your null hypothesis, can also take other values rather than 0, but more often than not we are basically testing that beta 1 is equal to 0 and beta 2 is equal to 0, and in that kind of a situation the F-stat that you will calculate for the joint hypothesis test will be through this formula over here. So, and then we will reject when F is large or larger than the F critical value, and we will fail to reject if the F stat calculated from this equation is smaller than the F critical value. So a couple of things that you will note from this formula for the F stat is that F stat is large when T1 or T2 is large, and that is simply because T1 square plus T2 square are in the numerator over here. The F stat corrects in just the right way for the correlation between T1 and T2. So like I mentioned earlier, the correlation between T1 and T2 will also affect the joint hypothesis testing. So the higher the T-stats, the T1 and T2, the higher will be the chance of rejecting the null hypothesis. Similarly, the higher the correlation between T1 and T2, the lower will be the chances of rejecting the null hypothesis, because the correlation term is basically being subtracted from the rest of the numerator. So the formula for more than 2 betas is nasty unless you use matrix algebra. So what does this mean? It simply means that if you are testing for hypothesis that beta 1 is equal to 0, beta 2 is equal to 0, and or beta 3 is also equal to 0, in that case you are testing for 3 restrictions, or you're testing for 3 different coefficients at the same time, and the joint hypothesis testing formula for F becomes really complicated, but the good thing is that STATA always can calculate that for us very easily, no matter how many coefficients we include as the regressor, no matter how many regressors we include in the regression equation, we can test for as many coefficients at the same time. So consider the special case that T1 and T2 are independent, and in large samples the correlation will between T1 and T2 will approach 0. So in that kind of a scenario, when the correlation will actually be equal to 0, your numerator will simplify and your denominator will also simplify to just 1 actually, and your total F-stat formula will simply become half multiplied by T1 square plus T2 square. If that is the case, under the null, T1 and T2 have standard normal distributions. We already know about that because we covered that in the previous lecture, that T1, which is the T-stat that you calculate for the coefficient beta 1, and T2 will be the T-stat that you calculate for the coefficient beta 2. Both have their both are normally distributed. So in that case, in a large sample distribution of the F-statistic, basically becomes the distribution of the average of 2 independently distributed squared standard normal random variables. So this is what the F-stat calculation boils down to in the case of larger samples when the correlation approaches 0. So how do we actually do this kind of a joint hypothesis test in STATA? So the post estimation command in STATA that we will use to run this joint hypothesis test goes by the name of test. So for example, if we have to test the joint hypothesis that the population coefficients on student-teacher ratio and expenditures per pupil are both 0, how do we do that in STATA? So we will basically run the regression first of all, and then we will use the command test and then type in student-teacher ratio variable, and also next to it the expenditure per student variable. And when we do that, we get the F-stat over here, which is 5.43. It is greater than 3, which is the critical F value. So whenever the F actual is greater than the critical F value, we can basically reject the null hypothesis that STR coefficient and EXPN STU coefficient are equal to 0. So the formula for the calculation of the F-stat that we looked so far assumes heteroskedastic error terms, but there's also a simple formula for the F-statistic that holds only under homoskedasticity. So you would think that why are we even discussing this? I mean, it's not very useful because we always are safe to assume heteroskedasticity in our error term. But there's an important application of the homoskedasticity-only F-stat because it can actually be shown with the help of a simpler formula using R squares from two different equations, and those two different equations are called the unrestricted equation and the restricted equation. So what we'll do is that we'll basically run two regressions, one under the null hypothesis, which is the restricted regression. So the restricted regression does not include the regressors for which the coefficients you are testing for in the joint null hypothesis. So for example, if your joint null hypothesis is that beta 1 is equal to 0 and or beta 2 is equal to 0, so the regressors which will estimate beta 1 and beta 2 will not be included in the restricted regression, while in the unrestricted regression all of the regressors will be included in the regression equation. So we'll basically estimate both of these regressions, the unrestricted one and the restricted one separately, and then we will get the R squares from both of these, and which will help us in calculating the homoskedasticity-only F-statistic. So let's explain this with the help of an example. So for example, if you are testing for the null hypothesis that the coefficient on student-teacher ratio and the expenditure per pupil on student is equal or are equal to 0, then you will have to first estimate an unrestricted population regression in which all of the regressors will be included, meaning the STR, expenditure per pupil, and percentage of English learners, all three will be included in the regression equation. And then we will do an estimation on the restricted population regression in which you will not be estimating the coefficients for STR, the student-teacher ratio, and the expenditure per pupil. So only the percentage of English learners will remain in this equation. So the number of restrictions under the null hypothesis is Q equals to 2 because we are testing for two coefficients, beta 1 and beta 2 are equal to 0, so which means that Q becomes equal to 2. So the fit will be better, meaning the R square will be higher in the unrestricted equation, and that is very simple to see because as we mentioned in one of the earlier lectures that R square always increases whenever you include more variables in the regression analysis, and that is simply because your explained sum of squares becomes higher, so your explained sum of squares become higher and your residual sum of squares becomes lower whenever you increase the number of regressors in the regression equation. But the question remains that by how much must the R square increase for the coefficients on expenditure per pupil and the percentage of English learners to be judged statistically significant. So this is the formula for the homoskedasticity-only F-statistic, and you can see over here that we are not really concerned with the correlation coefficient anymore. We are also not calculating the t-stats. What we are doing is that we are using the r square from the unrestricted equation, the r square from the restricted equation, the q, which is the number of restrictions, n, which is the total number of observations, k, which is the total number of regressors in the unrestricted regression. So using all of these will basically give us, if we plug in all of these numbers, it will give us the F-statistic for the homoskedasticity only F-stat. And the bigger the difference between the restricted and the unrestricted R squared, the greater the improvement in fit by adding the variables in question. So you can see that first over here we have the R squared from the unrestricted equation minus the R squared from the restricted equation. So if there is if there is a substantial improvement in R squared when we include the variables which are part of our null hypothesis, then we can say that including those variables actually adds to the regression, which would also mean that those the coefficients for those regressors are not equal to 0, meaning we can reject the null hypothesis easily if there is a higher difference between the R square obtained from the unrestricted and the restricted equations. Just putting this into context with the help of an example, we basically actually do estimate the two equations, the restricted one and the unrestricted one. And the R square that we get from the restricted one is 0.4149, from the unrestricted one is 0.4366. K, which is the number of regressors, 3 in the unrestricted equation, and Q, which is the number of restrictions. So if you plug in all of these numbers into this formula over here, we will get the F-stat of 8.01. If you compare this F-stat with the heteroskedasticity robust F-stat, the heteroskedasticity robust F-stat is a much lower value for the same hypothesis, for the same null hypothesis. It will be 5.43, but when we compare it to the homoskedasticity only F-stat, this one is a higher number than the heteroskedasticity one. So the summary is that the homoskedasticity only F-statistic rejects when adding the two variables increases the R square by enough. So if the errors are homoskedastic, then the homoskedasticity only F-statistic is accurate, but if the errors are not homoskedastic, meaning they are heteroskedastic, then the large sample distribution of the homoskedasticity only F-statistic is not accurate. So once again, if there is heteroskedasticity present in the error term, we cannot rely on this formula over here, and we will have to revert back to the earlier formula, which also relies on the correlation between T1 and T2. So that will be the case when there is any presence of heteroskedasticity in the error terms. So your regression printouts might refer to the F distribution. So what this simply means is that if the 4 OLS assumptions hold, along with the assumption of homoskedasticity and the assumption that your error terms are normally distributed, then the homoskedasticity only F-statistic has the distribution which can be written like this. So remember that when there is heteroskedasticity and then and when we have to refer to the F-stat formula which accounts for heteroskedasticity in the error terms, this is not the distribution that we are looking at. The distribution that we are looking at can be written as F q comma infinity. But if heteroskedasticity is what we are dealing with, if homoskedasticity is what we are dealing with, then the F distribution that we calculate the F stat for is as follows, becomes this one, where n is the number of observations, k is the number of regressors, and q is the number of restrictions. But the important point to note here is that as n approaches infinity, the F distribution which assumes homoskedasticity converges to the F distribution which does not assume homoskedasticity. So for q, in other words, for q, which is the number of restrictions, when it is not too big and when sample sizes are substantially large, meaning at least greater than 100, then the fq n minus k minus 1 distribution converges to fq infinity distribution. So many regression packages will compute the p-values for f-statistics, and you will also encounter F distribution in a lot of published academic journal articles, so which kind of shows the importance of this F-stat and the importance of jointly testing null hypothesis. And once again, why, this brings us back to our earlier question, like why do we even rely on joint hypothesis testing? Because just like the example that we started with, for example, if we are testing for the null hypothesis that financial resources matter or not, then maybe there are like more than one regressors which account for financial resources of the school, and then you will have to basically test them jointly in a hypothesis to see whether if any of those is not equal to 0. So this is the F distribution, which is the Fm infinity, and this is the distribution that we rely on whenever there is heteroskedasticity. So the degrees of freedom will basically be the number of regressors in the equation. So in a sense, the F distribution over here becomes Fk infinity, and that will basically determine what the critical value for F that we use. So for example, if we have two coefficients in the joint null hypothesis, then our degree of freedom will be 2, and if we are testing at the significance level of 5%, then our F critical value would be equal to 3. So the homoskedasticity-only F-statistic obviously relies on very strong assumptions that there is no heteroskedasticity present in the residual terms, which is more often not the case. But there's a historical context to the importance of this, and obviously this is a very old finding in statistics from the early 20th century. In those days there were no calculators, there were no computers, so, and data sets were also pretty small because data collection was not very advanced in that age. So people used to rely on this distribution, and this distribution, the homoskedasticity only F distribution, was considered a major breakthrough in statistics. But now all these statistical softwares rely on the F distribution, which does not assume homoskedasticity. So the strong assumptions of homoskedasticity were a minor price for the breakthrough and the ease that this kind of a distribution provided, because we could simply just look up this table to find out whether our calculated F-stat is greater or less than the critical F-stat, and then whether we can reject or fail to reject the joint null hypothesis. And keeping this historical legacy alive, a lot of modern softwares will actually calculate homoskedasticity-only standard errors and F-statistics unless we actually tell the software that we are assuming heteroskedasticity. So for example, as far as standard errors are concerned, you have to type in comma robust in order to tell STATA that you are assuming heteroskedasticity in your error terms. So just to summarize the homoskedasticity only F-statistic, they are justified only under very strong conditions of no heteroskedasticity. And the other point is that when n is greater than equal to 100, this distribution actually converges to the heteroskedasticity F distribution. But for small n, in cases when data availability is a concern, when data collection is a concern, when your sample size is usually small, researchers still rely on this homoskedasticity only F distribution because it has larger critical values, and in that sense is more conservative. Also, you can say it's more accurate. To further summarize the testing of joint hypothesis, the one at a time supposedly common sense approach is not really accurate because it rejects it incorrectly rejects the null hypothesis more than 5% of the time, when we want it to be incorrectly rejecting the null hypothesis only 5% of the time. And the heteroskedasticity robust F statistic is built into STATA, and you can just simply use the test command to use that. For large n, the F statistic is distributed with the distribution FQ infinity. That is what we will mostly rely on in this course and even in our data analysis in STATA. The homoskedasticity only F statistic was important historically, but in this day and age when calculation of F-stats and hypothesis testing have become very easier with basically a press of a button, is not as important as before. So just as we can jointly test the null hypothesis that beta 1 is equal to 0 and beta 1 and beta 2 is equal to 0, we can also find the need to sometimes have a null hypothesis that that two coefficients are equal to each other. For example, if we estimate this equation over here, we can test the null hypothesis that beta 1 is equal to beta 2 versus the alternative hypothesis that beta 1 is not equal to beta 2. So this is slightly different than the joint hypothesis testing that we were doing before, because this hypothesis testing imposes a single restriction on multiple coefficients. Because it's not a joint hypothesis with multiple restrictions, so you can compare this null hypothesis that beta 1 is equal to beta 2 with the null hypothesis that beta 1 is equal to 0 and beta 2 is equal to 0. So in this kind of a situation, you have two restrictions, but this classifies as only one restriction. So there are two methods for testing single restrictions or multiple coefficients. So you can either rearrange the regression equations or you can perform the test directly. So option number 2 is usually included in all the statistical softwares, including STATA, and you will pretty much use the same command test, but the syntax will be slightly different. You will write test, the first variable equal to sign the second variable, and it will STATA will basically test whether the two coefficients are equal to each other. But we will take a closer look at the first method, which is rearranging the regression equation in this slide. So, for example, if this is the regression equation that we are estimating, we have two variables over here, x1 and x2, and both obviously have their separate coefficients, and that is what we are testing for, that beta 1 is equal to beta 2 versus the alternative hypothesis that beta 1 is not equal to beta 2. When that is the case, if we simply add and subtract beta 2 x1I to this initial regression equation, we can simplify the equation to this equation. So remember, what you have to do is that you have to add and subtract beta 2 x1I. When you do that, you get this equation over here, in which the coefficient of x1I becomes beta 1 minus beta 2, and our second variable basically becomes the sum of x1I plus x2I, and beta 2 becomes the coefficient of that variable, which we will call W. So essentially what you need to do is that you have to construct a W variable, which is the sum of x1I plus x2I. Construction of this kind of a variable in any software, including STATA, is very easy. It's just with the help of one single command, you can calculate this variable W. While this coefficient, gamma 1, is equal to beta 1 minus beta 2. So beta 1 minus 2 minus beta 2 becomes really important, because that is essentially what we are testing for. So for example, if we are estimating this equation over here, and we actually test for the null hypothesis that gamma 1 is equal to 0, and the alternative hypothesis that gamma 1 is not equal to 0, when we are testing for gamma 1 is not equal to 0, we are essentially testing that beta 1 is not equal to beta not. Beta 1 is not equal to beta 2. So we'll take a better look at this in the next slide. So the original equation is as follows over here, but if we have to test for the null hypothesis that beta 1 is equal to beta 2 versus the alternative hypothesis that beta 1 is not equal to beta 2, we can rearrange the equation in which gamma 1 will basically be equal to beta 1 plus beta 2, while Wi is the sum of x1I and x2I. And when that is the case, our hypothesis testing becomes very easy, because we are back to testing the null hypothesis for one single coefficient, which in this case is gamma 1. So we can simply test for the null hypothesis that gamma 1 is equal to 0 versus the alternative hypothesis that gamma 1 is not equal to 0. And while doing this, we are essentially saying, when we are saying gamma 1 is equal to 0, we are essentially saying that beta 1 minus beta 2 is equal to 0, which means that beta 1 is equal to beta 2 becomes our null hypothesis. So these two regressions from equations A and B have the same R-square, the same predicted values, and the same residuals, but the only thing which becomes easier now is that the testing problem becomes very simple. You can test whether gamma 1 is equal to 0. So you'll basically need to simply calculate the t-statistic for gamma 1 and compare that t-statistic with the t-critical value and figure out whether you can reject or fail to reject the null hypothesis that gamma 1 is equal to 0, which essentially means that whether beta 1 is equal to beta 2. So the second method is much more simpler when you have access to some sort of a statistical software. If you are testing for beta 1 equal to beta 2 in STATA, you will simply write test. You will type the variable which generates beta 1 equals to the variable which generates beta 2, and it will basically give you the result for the null hypothesis that the coefficient of student-teacher ratio is equal to the coefficient of expenditure per pupil. So pretty much the same command, test, will do joint hypothesis testing with more than one restriction, and also with joint hypothesis testing for with only one restriction for multiple coefficients. So similar to the confidence interval, the idea of the confidence interval for one single coefficient, confidence interval sets can also be generated for multiple coefficients. So what is a joint confidence set for beta 1 and beta 2? It simply means that it's a set of values of data that contains the true coefficients in 95% of hypothetical repeated samples. You can also say that the set of coefficients, the set of coefficient values that cannot be rejected at the 5% level of significance is what the joint confidence set will be constructed of. So let beta 1 naught and beta 2 naught be the heteroskedasticity robust F-statistic testing the hypothesis that beta 1 is equal to some null hypothesis and beta 2 is equal to some null hypothesis. So then the 95% confidence set will basically be the F-stat that you calculate from the t values which you generate from beta 1 and beta 2, and that F-stat should be less than 3 in the case of two restrictions, and you can look up that value or you can look at that value of 3 for the 5% significance level when you look under the restrictions 2 in the F distribution table. So this set will have the coverage rate of 95% because the test on which it is based has size of 5%. So it will be only 5% of the time that this test incorrectly rejects the null hypothesis when the null is actually true. Or you can also say that 95% of the time it won't reject the null hypothesis when the null is true. So once again we get back to this formula to calculate the F-stat, and if the F-stat that we calculate for beta 1 and beta 2 is less than equal to 3, we can fail to reject the null hypothesis. So if we plug in the values of T1, T2 and the correlation coefficient in this formula for F-stat, we basically get this formula over here. So T1 can be written like this, T2 can be written like this. Sorry, this is for T2 and this is for T1, and this whole algebraic term can be written as follows. So if you look closely to this whole segment of the F-stat formula, this is a quadratic form, and because of this quadratic nature of this algebraic term, the boundary of the confidence set, which is F equals to 3, becomes an ellipse, and we can show that better graphically. So beta 1 hat and beta 2 hat that we calculate are right at the center of this confidence set, which is and they are equal to minus 0.29 and 3.87. So let's suppose if we are testing for the joint hypothesis that beta 1 hat and beta 2 hat are equal to 0, we will basically look at this point over here, and this point is outside the confidence set. So we can safely say that we can reject the joint null hypothesis that beta 1 hat is equal to 0 and beta 2 hat is equal to 0 by looking at this ellipse confidence set on the graph. So this final section of the lecture covers the variables of interest, control variables, and conditional mean independence. So as researchers, we want to get an unbiased estimate of the effect of test scores of changing class size, holding all the other factors constant, which can affect the test scores of students. And one of those factors might be outside learning opportunities. For example, children from more affluent backgrounds can have access to museums, libraries, they can go on trips, learning trips more often. Parental involvement for those kids might be higher, which can all really contribute to higher test scores eventually, to higher cognition in a sense. So if we could run an experiment to basically just isolate the effect of student-teacher ratio on test scores, we would randomly assign student-teacher ratios to different students through the help of a randomized control trial, which will basically ensure that our expectation of U given the student-teacher ratio is actually equal to 0, because every other attribute will be assigned randomly apart from even the student-teacher ratio will be assigned randomly to students with the help of a randomized control trial. But we have already discussed before that that is more often not the case, because more often than not you'll be working with some sort of an observational data, which would mean that your U will depend on additional factors such as parental involvement and knowledge of English, etc., etc. So if you can observe those factors, meaning you can get actual data for some of those variables which might be part of your U, your residual term, for example, percentage of English learners in the classroom or in the school district, then you can include them in the regression. But more often than not, you cannot observe all of these omitted causal factors. For example, parental involvement might be one factor which would be really hard to control for, which would be really hard to include in the regression, because data on parental involvement is just hard to come by. So in this case, you would be better off with using control variables which are actually correlated with these omitted causal factors, but which themselves are not causal. So what does that really mean? So control variable W is a variable that is correlated with and controls for an omitted causal factor in the regression of Y on X, but which itself does not necessarily have a causal effect on Y. So does not necessarily, meaning it can have a causal effect on Y, but the important thing is that that it is also correlated with an error term. So for example, let's try to figure out which ones of these variables in this regression equation are control variables and which ones are variables of interest. So percentage English learners in the school district can be thought of as a control variable. Why is that the case? Because it is controlling for the affluence of the household, because more often than not, immigrant families will be the students from or children from immigrant families will be the ones who will be enrolled in English learning programs, and more often than not, immigrant families will be less affluent. So in a sense, percentage of English learners is correlated with the error term, because the error term includes affluence of the household. Similarly, LCHPCT, which is the percent of students receiving a free subsidized lunch, can also be considered a control variable, because this is also correlated with the affluence, which is part of the residual. And that is because only students from low income families are eligible for a free subsidized lunch or school lunch program. So then what becomes the variable of interest in this, from this equation? The variable of interest would be the student-teacher ratio. Which variables are control variables? Do they have causal components? What do they control for? These are the questions that we will try to answer in the next slide. So the student-teacher ratio is the variable of interest, while the percentage of English learner probably has a direct causal effect, because if the student is enrolled in an English learning program or English learning course, it probably means that his test scores might be lower, because if you don't have a full grasp of the language in which the test is being conducted, you will probably have a lesser chance to ace that test. Similarly, LCHPCT is also a control variable, which might have a causal effect, because obviously if you are eating well, it should add to your learning and eventually to your test scores. But it is also correlated with income or affluence, which is part of your residual, because because students who are part of this program might not belong to affluent households. So it's both a possible causal variable and a control variable. So there are three interchangeable ways in which you can define an effective control variable. So the first one is that an effective control variable is one which, when included in the regression, makes the error term uncorrelated with the variable of interest. So what you are trying to do is that you are trying to take away from the correlation between the error term and our variable of interest, and basically trying to find a control variable which is more correlated with the error term than the variable of interest. Then another way of describing a control variable is that holding constant the control variables, the variable of interest is as if randomly assigned. So basically we are trying to get as close to a randomized control trial outcome in which everything else is randomly assigned. All the attributes are randomly assigned. And so the third and final way in which a control variable can be defined is among individuals with the same value of the control variable, the variable of interest is uncorrelated with the omitted determinants of y. So once again, the variable of interest, we want that to be not correlated with the error term, while we want our control variables to be correlated with the error term. So control variables need not be causal, and their coefficients generally do not have a causal interpretation. What does that really mean? So if you look at this regression equation over here, the coefficient of LCHPCT, which is participation in the school lunch program, is negative. So in a sense, if you look at it, if children are eating better, if they are part of this program, it should add positively to their test score. But why is this coefficient a negative coefficient? Is simply because this coefficient is actually capturing the affluence or the lack of affluence of the students which are part of this program. So if you are part of this program, it would mean that you probably belong to a less affluent household, which means that your chances of scoring higher on a test are actually lesser. So if we thought that this coefficient has a causal interpretation, it would simply mean that eliminating the school lunch program will have a better outcome for test scores. But you can try to basically form a policy around that, but that policy will pretty much be wrong, because you will be advocating for eradicating the lunch school program by saying that eradicating the lunch school program will be better for the test scores of students, when this lunch school program is actually correlated with the error term, in the sense that it is correlated with the part of the error term which shows the affluence of the household, and that's why this does not have a causal interpretation. Because remember, the first assumption of least squares is that if your x variable is correlated with the error term, you cannot get a causal interpretation from the coefficient. So now we will take a look at the condition of conditional mean independence for control variables. So since we have already established that the control variable is ideally correlated with the error term, meaning, for example, the lunch school participation is correlated with the part of the error term which is related to the affluence of the household, it simply means that that control variable does not really follow the first least square assumption. So if the first least square assumption does not hold, then what does hold, or what takes place of that first least square assumption? So the condition which actually holds in the case of control variables is the condition of which is called conditional mean independence. So given the control variable, the mean of u doesn't depend on the variable of interest, and we can show that mathematically as well. So let x denote the variable of interest and w denote the control variable. So the control variable w will be an effective control variable if the conditional mean independence holds. What that simply means is that the joint expectation of u given x and w, given your variable of interest and the control variable, if it is equal to just the expectation of u given the control variable, this condition is called the conditional mean independence. So essentially what we are after is that if the control variable is sufficiently correlated with the error term, it can take away the correlation, it can take away from the correlation of the variable of interest and the error term, and that if a control variable does that, in our eyes, that is the form of control variable which is the ideal control variable to include in our regression equation. So if w is thought of as a control variable when being included in the regression equation, then the condition of the conditional mean independence, which is written like this, actually takes place the first least square assumption that the expectation of w with u is equal to 0. So that goes away. Instead of the first assumption, this assumption takes place or can be replaced. So consider the regression model which is shown by this equation, where x is the variable of interest and w is an effective control variable. Let's suppose that the condition of mean independence actually holds, and in addition to that, the second, third and fourth least square assumptions also hold. So the second least square assumption is of IID, independently and identically drawn. The third one is there are no major outliers, and the fourth one is of multicollinearity. So if all of these assumptions hold along with the condition with the assumption of conditional mean independence, then it would mean that beta 1, which is the coefficient of the variable of interest, will have a causal interpretation. It will also mean that beta 1 hat will be an unbiased estimator. It will also mean that the coefficient on the control variable beta 2 hat is in general biased, and that is simply because it is correlated or W will be correlated with the error term. So how do we specify a model? How do we find the right model? So first of all, we have to identify the variable of interest, and that will be driven by the economic theory. Obviously, whatever our variable of interest is should have an economic relationship with the dependent variable as far as the economic theory is concerned. So that is our first goal. So we have to identify the variable of interest. So apart from that, think of the omitted causal effects that could result in omitted variable bias. So obviously in most of the relationships you can think of factors which will be part of your residual term, and though that residual term will also be correlated with your variable of interest. So it would mean that you will have the problem of omitted variable bias. So in that case, include those omitted causal effects if you can, and if you cannot, then find variables which are correlated with those causal effects, and those variables can serve as the control variables. And the control variables are effective if the conditional mean independence assumption holds, meaning that if U is uncorrelated with the variable of interest, meaning in our example student-teacher ratio, once the control variables are included. So the correlation between U and our variable of interest actually goes away because of the correlation between the control variable and U, which actually becomes stronger. And that is and then that kind of a model can serve as our base or benchmark model whenever we are trying to find the right or correct model specification. So after that, after finding that base model, you can also specify a range of other alternative models which include different regressors, additional regressors, and some of those can also be control variables, which once again are correlated or possibly correlated with the error term. So when you do that, you can estimate the regression equation with your base model and with your and with your other models with plausible alternative specifications. And those models with alternative specifications can serve as your sensitivity checks, meaning how does the inclusion of those other control variables affect the coefficient of your variable of interest. If it varies widely, it would mean that your coefficient of variable of interest is not a stable coefficient, and that is a cause for concern. If it does not vary widely, it would mean that it's a very consistent estimator. So another important point is to use judgment when you are including control variables, meaning the control variables should also be included based on some sort of economic theory, economic theory which derives the correlation between the control variable and the residual. So it's not simply a mathematical or a mechanical formula, so you have to apply the economic theory. And don't just try to maximize R square, because as we have mentioned before, even if the control variable is not an appropriate one, the R square will increase whenever you include an additional variable in the regression equation. So, which brings us to an interesting point about the measures of fit, including R square and adjusted R square, that don't fall into the trap of maximizing the R square or the adjusted R square. This can be shown with the help of 4 different cases. So, a high R square or adjusted R square means that the regressors explain the variation in Y. Is that true or false? It is not always true, because a high R square or adjusted R square does not really mean that the regressors always explain the variation in Y. So think about this for a second. So R square will always increase whenever you increase the number of regressors, even if they make or do not make any sense in the model. So in just including more regressors will increase the R-square, but does not really mean that it explains the variation in Y. A high R-square or adjusted R-square does not mean that you have eliminated omitted variable bias. So there's no guarantee that you have eliminated omitted variable bias when you have a high R-square. And similarly, there is no you cannot really say with a low R-square that you have not eliminated omitted variable bias. Omitted variable bias should be, once again, the presence of that should be dictated by your economic theory surrounding the econometric model. Similarly, a high R-square or adjusted R-square does not mean that you have unbiased estimator of a causal effect beta 1. So once again, the causal effect will be determined by whether whether the variable for which the coefficient beta 1 is actually correlated or uncorrelated with the error term. So that will determine the causal effect. And the last one is that the high R-square does not mean that the included variables are statistically significant. This must be determined using hypothesis test. So once again, even if you include a control variable which is not significant, it will still lead to a high R-square. So which essentially means that a high R-square does not really mean that the variable that you have included, which has led to the high R-square, is actually a significant yields a significant coefficient. So to summarize our model specification, first of all, you have to identify your variable of interest. Then you have to think of the omitted causal effects that could result in omitted variable bias. So think of all the factors in your residual, in your error term, which can be correlated with your student-teacher ratio, such as whether the students know English, whether there is parental involvement, what is the affluence level of the household, and etc., etc. Try to include the omitted causal effects if you can. If you cannot, try to find control variables which are correlated with those causal effects. Once you do that, you will take away from the correlation between the error term and the variable of interest, and that will be a good thing because it means that the control variables are actually doing their job. Also, when you are done with specifying your base model, specify a range of plausible alternative models which include additional control variables. So just to see which ones are more significant than others, because that will give you a good idea of whether a control variable is showing a causal effect or not, and also like how it is actually affecting your dependent variable. And estimate your base model and your plausible alternative specifications as sensitivity checks, meaning just to see whether your coefficient of your variable of interest varies a lot when you are including different control variables or not. If it does not vary a lot, that's a good sign. So this is a simple scatter plot which shows the correlation between test scores and the different regressors, meaning the percentage of English language learners, the percentage of students with the school lunch program, and the percentage of students which qualify for income assistance. And all of them show a negative relationship between the regressor and the test scores, which makes sense. So, but it does not necessarily mean that including all of these as control variables will be a good idea, and that's why you need alternative specifications in order to see which ones of these might actually be better as far as capturing the correlation between the control variable and the error term. So if you have a number of regressions and you want to report them, meaning you have different model specifications, which are your alternative model specifications, just writing down the equation and writing the coefficients and standard error in the form of equations can become really difficult to read. So a table of regression is the way to go about it, and the table of regression should actually summarize the estimated coefficients, the standard errors, the measures of fit, the number of observations, the relevant F-statistics if they need to be reported. So a good table of regression summarizes all of these key factors very nicely and very clearly to the reader. And this is an example of a classic and self-explanatory kind of regression results table, which is more often seen in academic writing. So for example, model 1 can become your base model in which you only have your variable of interest, and after that you're basically adding percentage of English learners as one of your control variables, and there is a common control variable in the other model specifications. And after that you're basically testing for testing to see how the inclusion of the control variable of subsidized lunch changes your coefficient of student-teacher ratio, and when you exclude this one and include the percentage of students on public income assistance, how does that affect your student-teacher ratio? And finally, in the last model specification, you include all the control variables along with your variable of interest to see how that affects your student-teacher ratio. So if I was the researcher of this project, I will be very happy because in model specifications 2, 3, 4, and 5, the coefficient of student-teacher ratio does not change by a lot, which means that it is pretty consistent and is pretty stable. So to summarize the case of multiple regressions, multiple regression allows you to estimate the effect on y of a change in x1 holding other included variables constant. If you can measure any sort of causal variables, you should include them in order to avoid omitted variable bias. But if you cannot do that, you should look for control variables which are correlated with those causal effects. And that will be a good thing because that will actually take away from the correlation between the variable of interest and the error term. And it's not a mechanical formula, there's not a maths or your regression results should not be guiding this. A good economic theory should be guiding your judgment as far as your model specification is concerned. So basically find out a base model based on the economic theory, and then try to do the sensitivity analysis, meaning try to estimate different alternative specifications to see whether your coefficient of the variable of interest changes by a lot or not. If it does not change by a lot, that is a good sign. So that is all for this chapter, which deals with the hypothesis test and confidence intervals in multiple regression. I hope you guys enjoyed this lecture and it added to your knowledge of multiple regression. I thank you all for listening, and see you guys next time.